It's my pleasure to introduce Mohammad Saadatfar from the University of Sydney. He's going to tell us about order, disorder, transition in experimental sphere packing. Thank you, Mohammad.
Thank you, Adil. Good morning, everyone. Thank you, Adil, and thank you, Simon, for inviting me. So this is certainly a lot cozier and smaller than the last couple of weeks, at least. I don't know how the first week was, but yeah, so this is a picture from the second week, the first day of the workshop. And so thanks so much for inviting me. It's been certainly a pleasure to catch up with old friends and make some new ones. And thanks to INI for partially facilitating my trip as well. So yes, I work in Sydney now, Sydney University. And I also have affiliation to the ANU, Australian National University, where I worked for more than 10 years. And the work that I'll present to you today has been initiated and mostly done at ANU, and it was really a labor of love. So this is something that we did with a bunch of colleagues, students, postdocs, and technicians, and lots of people who were curious about this topic that I will be talking to you today. So, so one of the joys for us has been that we just were curious and we were having fun, and we still do. So some of the results that I show you today, they are from 10, 15 years ago. And the trickle just continued and trickled over many years and continued making us excited and curious about this topic of structural kind of transition in from when sphere packings undergo transition from order to disorder. So I think some of you guys might have been in Australia. For those who haven't, that doesn't seem to be working here for me. So this is supposed to, give you a little pleasure. I can't seem to be getting rid of this now. Anyhow, so below what you see is a picture of the ANU, Australian National University, where I work. Gerd also worked there as a PhD student. And I think, Simon, you've been there, right? Been there, yeah. And it's a really beautiful campus, beautiful city. Not quite as small as Aberystwyth, but certainly charming and also quiet. And so that's what we love about ANU. And so underneath what you can't see, the picture here, what you can't see is a picture of the School of Physics, where we have the facility to do some experiments and where most of this research was done. So I leave it to your imagination to figure out. And so what you see here is what I will be talking to you about today. So it's a really nice and cozy gathering now. So hopefully it will be more engaging. And I'll try to go slower, not too slow, so we miss lunch. So hopefully I can tell you by the end of the talk what this picture is about, how it came to exist, and what kind of stuff we can see inside of this kind of experimental packing. It may not look much like an experimental packing. It's a reconstruction of the experiment. So this is one of the aspects of the talk today that I will walk you through how we obtain such structures. So we learned over the last few days, a couple of weeks maybe, that the best way you can pack together spheres, that kind of appeared again. So let's see. Oh, good. So is what's known as the kissing number. So you have a central sphere. So from here on, what we talk about for all intents and purposes, we are talking about more or less identical sized spheres. So we are talking about mono-size packing of spheres. And wherever we have some sort of polydispersity, I will mention that. So the case for single-sized spheres, we know that you can pack 12 spheres around the central sphere, and you can create the most dense local packing, right? And so this kind of arrangement forms an icosahedron if you place the centers of each sphere on the ecosahedron, you will see that you have this kind of really compact, really nice, fully dense local structure that unfortunately doesn't fill the space, and it leaves, if you try to put them together, they will leave some gaps, and this structure is frustrated. So we also learned that the best way to fill the space and still try to maximize the available space in terms of packing density is a crystal formation of hexagonal packing. So either FCC or HCP. Okay, so this is fairly classical kind of view of sphere packing in theoretical way, and is pretty much known. Okay. And the proof has been in the making for a long time, which took more or less 400 years. And so but this is something that most of you would be familiar with, so I won't go through the details here. But we now are confident that the conjecture that Kepler laid out some 400 years ago is correct. So the densest packing of spheres in 3 dimensions that can form a crystal pattern that fills the space is either FCC or HCP, some sort of hexagonal packing. And this is nice, but we know that the densest packing that we can achieve and still fill the space is either FCC or HCP with a packing density of around 74%. Okay, and this is the ideal or optimal packing that you can possibly achieve and still fill the space. But in reality, we know that this is what happens when you put together a bunch of more or less identical spheres. And what's really nice is that depending how smooth these watermelons are, you get a packing density ranging between 55% to 60, more or less 64, 65%. Meaning the packing, the disordered packing that you achieve here is only and only dependent to the smoothness of the watermelons as well as the shape. So these are not the parameters that we will be discussing today, but what I would like you to note here is that these random packings of spheres are highly reproducible. So if you have certain density, if you have certain friction, smoothness of the watermelons, and if you have certain size, fixed size of the watermelons, regardless of how many times you repeat this experiment, you will always get a certain packing density.
Is that the definitive watermelon packing density there?
So the beauty of sphere packing is that it's highly reproducible.
Okay, sorry.
So if your question is about this, that's not true. So thanks to some Japanese invention, you can actually practice a lot more. However, so what really fascinates people in the sphere packing community is that this packing is highly reproducible, despite being or seemingly fully disordered. Okay, and the packing density that you can achieve by stacking them disorderly is a point that can only and only depend on a very few parameters. So this is well known. People have been working in this area for decades. And in fact, this is really one of the reasons why these sphere packings can be used for as a model to model a lot of soft matter phenomena. And so because simply by tuning one single parameter, which is the packing density, right, you can transition across state of matter. Okay, and so you probably have seen this this picture by Polycon and colleagues. So this really nicely captures what happens when you just change or tune the packing density of sphere packing. So you basically transition from 3 states of matter. Okay, so this is a part that a lot of people have worked on, and this is also something that we worked on some 15 years ago. So in this part, you basically transition from a liquid-like structure to something that resembles more like solid. Okay, so this is known as disordered jam packing of spheres. Okay, so and it only depends on a very few parameters. But regardless of what you do, you always end up with a disordered packing of spheres that are highly reproducible. So this is really the key why this part is so fascinating. Okay, but there's only so much you can do as far as you pack these spheres disorderly. And the limit of how much densification you can achieve while still having disorder in the system is around 64%. Okay? And that's known as the Bernal density. So beyond the Bernal density, you have no choice but to introduce some sort of order in the packing. Okay, so so you go beyond the Bernal density, and a lot of things happen here, and eventually, in an ideal world, you will arrive at either FCC or HCP structure. So what happens here in this range, around 10% of packing density, is what I will be talking to you today about. And also, I will try to reveal what happens during the transition from disorder to order at this point, or at any point along this range, where the structure transitions from jammed disorder to jammed, partially ordered, and fully ordered structure. So, good so far? Okay. So one of the earlier people who actually did some experiments, instead of just speculating about this, as you would know, is Bernal. Okay. So he did a lot of experiments back in the 50s, and he published some really interesting work. And I actually recently read his Nature paper again, which is a single author paper, but he acknowledges that a lot of students worked really hard. But he didn't include anyone. Back in the day, you could do that.
You know that Dennis spoke about Bernal, the very first day of the conference.
All right, I wasn't here.
Watch it on YouTube.
Okay, cool. So yeah, so it's fascinating what he did. So he actually created a lot of packing, a lot of experimental packing using steel ball bearings, so more or less zero friction, or close to very low friction, close to zero friction. And he managed to identify a highly reproducible packing fraction, and also identify that the structure is more or less disordered, and the contacts that you get is more or less in this range. Okay, so and besides that, he was also able, by reconstructing the packing through some balls and beam network, he was able to, in fact, plot the pair correlation function of such systems. And I can only imagine how hard it must have been to do that. But you know, that was really quite fascinating what they did. So that's one of the early experiments on hard sphere packings that attempted to understand the nature of jammed sphere packings and disordered packing of spheres. Okay. So in the same fashion, we also tried to do more or less the same. Okay. And we tried to do experiments that would go beyond Bernal's packing density. Okay, so this is really what this talk is about. So we start with a packing that is fully jammed, and its density of disordered density is as high as it can be, and so which is the Bernal density, and then we try to go beyond that. Okay, so our experimental protocol to achieve kind of higher density than Bernal density is quite simple. Well, it's simple now. So we played with quite a lot of protocols, and we realized this is something that more or less consistently works. So what we do, we put a few hundred thousands of these spheres, ranging from ball bearings to acrylic spheres and glass beads, in various kind of geometries. So here you see a cylindrical geometry, and then we subject this packing to intense vibrations, three-dimensional vibrations. So that means vertical as well as horizontal vibration. And what we realized that key for being able to create structures that have higher density than the Bernal density is that the structure is somehow sheared as well. So simply packing or one-dimensional compaction didn't seem to work always, or it wasn't really reproducible. However, following this protocol, we were able to create structures that certainly showed some order. Okay, so this is the cross-section of a spherical packing. And so this is another cross-section perpendicular to that one. And as you can see, there are ordered regions here and there. There are some seemingly disordered parts as well. But overall, we achieve a packing density that is greater than Bernal's density, but still lower than a fully crystal packing.
Up and down, side to side, correct, in and out.
Yes, so
Rotation.
So the side to side is essentially a circular edge. So there is rotation, that's right. And so we played with various types of geometry. So it's not just, so we use spherical of different sizes and cylindrical geometries of different sizes, different kinds of granular materials here. And the results were more or less consistent. So we were quite happy with this protocol. And so we have the frequency. So I get to that. So I won't really show you the details of the frequencies and all that, but it turns out that it's not that important. What is really important is the protocol itself. So you intensely vibrate it, and you force the structure to go through 2 stages. So annealing process for a second or 2, and then rapid quenching. So I have a video I show you, and that probably makes it a bit clearer. And by the way, all of these were done on Saturday mornings. So that's why I said this is really something that we do it out of love. So if I can play this. Right. So yeah, it's a cylindrical geometry, and we have about 300,000 grains in there. So we start with disordered packing, and then it begins to vibrate, while also circularly moving as well. So you don't really see that component that easily. So the top, we have a plate that has many holes in it, so the air can escape. The beads here are coated with graphene to avoid electrostatic charges, so they repel each other. So they don't repel each other. And as you can see now, it's intensely vibrated to the point of gasification. Okay. So this was the top of this the packing when we started, and now we go through a series of annealing and quenching. So it's still going. So this is really unnecessary to go for that long. So we realized that as long as you fully vibrate, intensely vibrate, and create some sort of gas. So that was annealing, and then rapidly freezing. Okay. Still going. So you end up with a slightly a more compact structure than you started. Okay. So at this point, we still didn't know whether we are really getting densification in the bulk. So, but on the surface, we could see some patterns forming, right? So, but that could mean also not much for the bulk. And so we had to peer through structure to access that. So is there any questions about the experiment?
Where did you get the spheres from? Are they just ball bearings that you buy commercially?
So what you see here is just acrylic beads. And so these are 1 millimeter acrylic beads that we just coated, not just really coated, we just poured some graphene into a container, so the graphene sits on top of them a little bit, not fully coating, but at least there's some residual of graphene. And we realized that that's actually quite important as well, because like electrostatic charges, so these are really light particles. It can really impact the process. So there are a few little tricks along the way, but the thing is that now we can reproducibly and routinely create partially crystallized packing or fully crystallized packing in some cases based on this protocol.
These are highly monodispersed, are they?
So monodispersed, yes, but they're about 1 millimeter in diameter, and there is a 0.5% polydispersity. And it's better than what we got from the supplier. So we found out this really nice low polydispersity later on through tomographic analysis, that they are actually more spherical than they were supposed to be. So yes, so it has very low polydispersity.
And do acrylic beads deform when they're pushed together?
They do to some extent, yes. So I also show you some results on that too. Cool. So again, the hard work that Bernal and his team did is really remarkable, and I appreciate it really deeply after I tried to reproduce some of that. Right? So they actually poured bitumen. So they created these kind of packing structures, so some sort of flexible membrane, and put a lot of steel beads in them, and while making sure that you don't create a lot of order. So they went through a lot of processes, and then they poured very gently bitumen into this membrane, and then once everything was cool and cold, so they removed these beads one by one, and they looked at how many contacts there are on each bead, wherever bitumen wasn't touching, right? And then they reconstructed this structure from that. And they did more than one. So that's really a lot of work. And I feel sorry for the students who did that and their names didn't appear on the paper. So that's really hard. And so we are lucky to have access to a tomography system. So essentially using X-ray, you can peer through any structure as long as they're not very dense, they're not made of lead. So this is quite typical, a schematic of a typical tomographic system. You have an X-ray source, you have a detector, which is sensitive to X-ray, and this is where you place your bead packing. And then you just take images, right? So non-destructively. So we are lucky. So one of the reasons that we were able to do this work was that we are, so the Department of Applied Mathematics at ANU is really one of the best places in the world that in terms of tomographic imaging and image analysis and producing the one of the highest quality images that we can possibly get. So really the quality is something that is more or less unmatched in the world. So we have a team that is fully focused on producing the best possible images. Okay, and this is just one of the machines, schematic of one of the machines. So we have quite a few of them. So this is how they look like. So that's your X-ray source, and this is your detector. And there are quite a few of these machines, and each kind of tailored for different applications. So for us, it was fairly straightforward. So we would create these packings somewhere very close to the machines, and then put them in the machine, and we would scan them. Okay. So what comes out from scanning this packing is our tomographic images. Okay, so you basically can do whatever you want with this with digitized version of your packing, and you can peer right through them. And this is slightly a time-consuming process. So the scan times are usually around 17 hours, more or less, give or take 3 hours maybe, and the spatial resolution you get is really good, in the sense that you can determine the contacts and also the diameters of each bead with extremely high accuracy. So the beads are roughly around 1 millimeter in diameter, and you have the voxel size of about 10 microns, meaning each bead can be represented by about 100 microns. Am I correct, or 1,000? So 100 microns, right? And so in order to find the centers, you simply find the barycenter of these spheres, which is made of close to 50,000, if I'm not mistaken. So you have 100, and the radius would be 50, and 50 power to 3 would be 500, actually, sorry, 500,000. So you can calculate the centers of each bead by averaging the barycenter of over 500,000 voxels. So that gives you access to an accuracy of nanoscale when it comes to calculating the centers of the beads. And slightly less accurate would be measuring the radii of the bead, because you have to deal with the surfaces rather than the volumes, but still you have nanoscale accuracy in determining exactly where the centers are, what the radii are, okay? So this is just two snapshots of two packing geometries that we had, so spherical and cylindrical. And so this is one of the packings that created the highest packing fractions. So we have more or less fully perfect packing with a packing density of around over 73%. And this is a partially crystallized packing with a packing density of close to 0.7. And yeah, so the polydispersity is about 0.5% at the. So that was more than 10 years ago. And so yeah, the technology has moved on really, really far in the meantime. So some of you might have seen the work by Francesco Moreno in Berlin. So they did some really nice experiments with on the coalescence of metallic foams. So these are molten aluminum foam, if I'm not mistaken, and they put them in synchrotron, and they watch them. They watch the metal basically forming a foam, okay, by blowing some bubbles into it or having some gas-producing agents in the mix. So the hardware has gone really far, and if you're using synchrotron, you have access to expensive facilities. You can take up to 200 or 300 tomograms a second. Okay, and so the same thing can be also applied to the sphere packs that I just talked to you about. And in principle, we should be able now to scan sphere packings dynamically as they crystallize. Okay. So, and I think they did something really amazing as well. So they focused on a very small region, and they were able to scan a few million a second, fully in full 3D. So they really fully resolved this issue of time-dependent tomography. And also on the software front, there has been recent advances. So this is a work by one of my colleagues, Benji Marks, and students. And so this is just a proof of concept. So they are able to fully reconstruct sphere packing by taking a single X-ray projection. Okay, so I didn't really run you through all the details of tomography. So you are supposed to take around 10,000 or so projections of the sample from different angles in order to reconstruct a 3D image. But here, using new algorithms, you can actually reproduce or reconstruct a 3D structure using a single X-ray projection. Okay, so that will increase your temporal resolution by 10,000-fold. So, yeah.
Provided you know that they're spheres.
So you need, yes, you need to have some a priori information. So you need to know that what kind of range of radii you're dealing with, and also at the moment, it's the certainty drops quickly if you go beyond 12 sphere diameters. So, but these things can be improved as well down the track. But yeah, so there's a lot of hope to actually do a lot of dynamic, really nice dynamic imaging with sphere packs as well. So this is what we get after scanning our partially crystallized sphere packings in the tomograms. So what we see is that, yes, there is bulk crystallization, but there's also some regions that are not fully crystallized. And so this is just one example. We scanned through many packings. So I think in total close to 60, if I'm not mistaken. And we see that, yes, so we see that, so the usual way of creating crystal structures in 3 dimensions is epitaxial or some sort of shearing. And we see that this protocol also produces bulk crystallization. So now this structure can lend itself immediately to any sort of statistical analysis. Okay, so so we have about roughly 300,000 grains, and these are just the internal grains. So in total, we have more. So we remove quite a few layers of boundary grains, so we can trust the statistic in the bulk. So we are confident that all the data that we have is from the bulk. So in order to dive deeper into what's happening inside the structure, so we basically compute the granular space using some standard techniques like Voronoi partitioning and Delaunay partitioning. And we look at both disordered packings and also partially crystallized packings, as well as close to fully crystallized packings. So I will run you through a few of the results that we have from either of these way of computing the space of granular materials, and we see that each of them yield a different type of result that help us understand the space of or the packing of spheres in a different way. Okay, so this is again a work that we did quite a while ago, and some of you might be familiar with this. So if you look at the disordered packing of spheres and compute the Delaunay space, Voronoi space around each grain, you can arrive at certain universality in a way that the distribution of the volumes around each grain follows a universal behavior, such as this one. Okay, and that is independent of the packing density of your packing, as long as you're within disorder. So this is really the key. Okay, so you can scale it by basically certain parameters, the minimum volume available, and you get this really nice behavior of the volume distribution. This is a big deal because up until then, we really had no idea how the volume distribution is within disordered packing of spheres. And for a long time, people, starting from Sam Edwards, they've been trying to understand or trying to formulate statistical mechanics for granular materials that are macroscopic. So the issue is that in macroscopic granular materials, we don't really, we are not able to explore the energy landscape as we can when we have Brownian motion. So the system is permanently out of equilibrium and it's dissipative. So there is really no proper statistical mechanics that describes that. So for thermal systems, we know that Boltzmann energy distribution is something that we can use and it works. But for granular materials, if we assume that V can be replaced by energy, we can have this volume distribution, which can help us understand granular materials in terms of statistical mechanics. So what's nice here is that you only have three parameters. There's V min, so there's the minimum volume available inside your packing. So that is the volume around the central sphere in your icosahedral packing. So the smallest volume that can be achieved. And there is the average volume. So this is calculated based on the Voronoi tessellation. And then there is this free parameter K, which defines your gamma function. Okay, so this gamma function turns out to fully describe and predict packings of disordered identical spheres. So, and there are some, so you can go deeper and find out what this K means. And this K for disordered packing turns out to be around 11. And it has its roots in specific heating granular materials. So I won't go into that in that direction that far. And the reason I show you this here because I want to draw a comparison with partially and fully crystallized packings. So if you repeat the same thing and for partially or fully crystallized packing, you will see that no such universalities can be found anymore. Okay, so again, partially because disordered packings are highly reproducible and you have disordered structure. But for partially crystallized or fully crystallized packing, you have your packing density for the same material, for the same sphere, for the same container can be more or less based on the protocol you have. Okay, so you end up getting this distribution of volumes based on the packing density that you achieve in the system. Okay, and so while you are increasing the packing density or decreasing the free volume in between grains, your standard deviation for each of these packing distribution is increasing, and that's what's shown here. So this is really quite important because this is what determines the value of K in the gamma function that I showed you earlier. And it turns out that the standard deviation of the volume distribution monotonically decreases as long as you are below Bernal packing. And then it increases rapidly between the Bernal packing and 68% packing density before it drops again rapidly. So the picture of this K for gamma function is quite complex when you introduce order in the system. So you can repeat the process for many packings. And what you get is that, yes, more or less for the disordered packing below the Bernal density, you have this value of K close to 11 for most of disordered packings. Then you have 3 transitions at 64, 68, and 72 that produce different value of K. So this K is connected, related to specific heat equivalent in granular materials. And in the same way as we define specific heat, amount of energy you give to the system to increase its temperature by 1 degree, for instance. So in analogy to granular materials, that's more or less what we do as well. So you intensely vibrate the system, you inject energy into the system, and you increase the temperature. And the temperature equivalent for macroscopic granular materials is what's known as compactivity. Right? So how compact the structure is. So it's not just the volumes around the grains, but it's also the compacts that the grains form during this evolution. So it turns out that both the volume and the compacts are really important if you want to understand deeper statistical properties of granular materials beyond Bernal. Okay, so this is just a snapshot to show you how the compacts evolve during this crystallization process. So what you have here is a large range of packing density, starting from the minimum disordered packing you can get all the way to a fully ordered packing. And so the blue here is our experimental packing, and the green is the theoretical prediction by Hernan Maxa and colleagues. So the geometric packing does increase quite monotonically as expected. However, if you look at the fluctuation of the contacts, so how many contacts per grain you have and how this evolves as the packing density increases, you get a much richer picture. So while the fluctuation remains more or less constant in the disordered phase, you start getting an increase up to 80% in contact fluctuation, meaning a lot of grains form and remove contacts continuously along the way. And that is deeply connected to this specific heat before everything drops down to much below the disordered region. So this is geometrical contact. So if you define a certain distance around the center of a grain, you just see which grains are in contact. So this is a mix of the grains that are exchanging forces plus the near contacts within certain distance. You can break it into a bit of the details and remove and basically extract the mechanical contact, both experimentally and using DEM. So Adil, answer to your question. So because we are able to recover bead diameters or radii at nanoscale, so we can tell how much they are deformed experimentally. And we can basically find out how much force is going through each contact, okay? And then you can, because you have access to all these centers and radii, you can simply import them into any DEM software and let the structure relax, okay? And also measure the forces based on that, right? And so you get a really good agreement between experimental measurements and also the DEM-based analysis. So the good thing is that once you have access to the structure by a DEM, you can play with other parameters. So 0.3 is the experimental packing. So this one, yeah. And so you can play with friction and see what role friction plays. So it's a really surprising but interesting picture that emerges from mechanical properties of such systems, right? So you get a rise and you have a plateau region where the mechanical contact does not change anymore. So the number of mechanical contacts remain more or less constant while the system is trying to figure out how to produce denser and denser local packing, and then it rises, okay? So this is good. So we have some understanding of the statistics of the system as it goes through this densification process, but we really wanted to understand what happens at the grain scale, okay? So this is when we turn to the Delaunay triangulation to actually identify the dense local arrangement of spheres and see what kind of patterns or structures are formed at that scale and how they respond to compactification or crystallization, okay? So again, we start with Delaunay and we identify or define dense local structure of arrangement of grains by identifying tetrahedra that have certain criteria. And there is a reason for this, because that's where that's below the peak of, I'm not showing it here, but that's below the peak of the distances between largest distance in any tetrahedra that's found in here. So if a tetrahedron is satisfying this condition, meaning the longest length or edge in the tetrahedron is less than 25% of the diameter, we consider that tetrahedron as a dense tetrahedron. And the idea is to see what kind of locally dense or evolution of this kind of dense tetrahedra we get as we go through the packing density, okay? And then we look at the graph that these dense local tetrahedra form in the sense that what kind of polytetrahedra they form at any given packing density. So polytetrahedra are aggregates of these tetrahedra that are made of more than 3, so 3 or more. So this is kind of more or less accepted because 1 is isolated, 2 you can have just face connected or isolated by pyramids, but if you have more than 3, you consider that you have a polytetrahedra. So what you get is a branch kind of graph that is made of lots of rings and lots of structures and lots of branches. And so that's how we go about and try to understand what kind of locally dense packing we get. So what you see here is a picture of these rings that are formed in this polytetrahedra. And so the 5 ring would be naturally frustrated. However, because we have this kind of pretty loose definition of dense tetrahedra, they form a full ring, as you will see. And so these are snapshots within our packings. In a few places, you can see that you have rings of 5, you have rings of 6, which are rare. You have a lot of rings of 5s, and you have a lot of branches. You even have some icosahedra that are formed, a bit incomplete, but you can identify them. So I'll go a bit quicker. So you can peer into this graph and try to identify what kind of rings, for instance, you have. And it turns out that rings of 5, they are the most abundant species. Despite being geometrically frustrated, your structure is mostly made of 5 rings, okay? So which are these ones? You also have some rings of 8, which are essentially rings of 5 that are connected, but with a missing link in the middle. Okay, so again, so these are really related to rings of 5. And as you increase the packing density, so these rings of 5s basically disappear because they're geometrically frustrated. They have to break up to form full crystal. Then you can start looking at the significance of these polytetrahedra. Okay, so I will probably skip a few slides here since time is short, but so what you see in red here is the fraction of grains that are involved in the formation of the polytetrahedra. Okay, so when you are in the disordered regime, as you densify all the way to Bernal density, more and more grains join up the polytetrahedra picture that I just drew for you, to the point that at Bernal density, nearly 90% of all the grains are a part of this polytetrahedra. Okay, and if you look at these dense tetrahedra, not polytetrahedra, just individual or bipyramid tetrahedra, at Bernal density, what you have is 100% of grains are involved in polytetrahedra. Okay, so the picture begins to emerge that densification within the disordered regime is by formation of polytetrahedra and mostly by forming rings of 5. Okay, and of course, at that point, at Bernal point, you have, if you are going to densify the system more, you have no choice but breaking up these polytetrahedra, especially the rings of 5, so you can form some crystals that can fill up the space, like FCC or HCP, and you get this rapid decline of the polytetrahedra aggregates. So I will skip the next one, so I can talk to you about some other aspects of these packings. I can pause here for a half a minute or a few seconds if you have any questions. Good? Yes?
So you've chosen the ratio of 25%.
Right.
How sensitive is what applies to that?
Not so, so that's why we chose that. So it shows the value that doesn't change the results. So if we go to, let's say, 5% instead of 25%, we do see some differences. So we have some dispersity, but we also have grains that are not really fully dense locally. We're not forming a fully dense arrangement locally. So we wanted to include them as well. So by about 20% on either side, we see no change. So the reason we chose that is because when you plot the maximum length of tetrahedron and find it and look at this distribution or histogram, you will see that they peak around 20, between 20 to 25. So what I showed you so far is a polytetrahedral aggregate picture made of dense local arrangement of grains, basically forming tetrahedra. Okay, but a packing is more than that. So there is a lot more happening that we may not be able to capture by looking at only and only dense tetrahedra. And that's why we started looking at persistence homology. Persistent homology is a mathematical tool that has been around for quite a while, so I won't go through a lot of details here. So the idea is that you put in a point pattern and you do your homology calculations, and what comes out is a few topological features like connected components, holes and cavities, okay? And it's a big deal because it is a topological measure and it's insensitive to a lot of changes like rotation, translation, etc., but also it's robust to noises. So it's really suited to peer into large volumes of data that come out of experiments. And you can easily filter out noise in such systems, okay? And what comes out is a persistent diagram, usually known as PV, and it's made of two perpendicular axes known as death and birth, ominously. And so you basically try to track what kind of topological features are born at what stage and what kind of topological features die at what stage, okay? So maybe in 2 seconds, I'll run you through this. So imagine you start with these dots, black dots, as the centers of your packing, for instance. This is a 2D representation. So persistence homology essentially filters from 0 radius to infinity and basically forms a circle around each point and continuously increases this radius all the way to infinity, and along the way tracks what kind of loops, for instance, are formed, okay? So at alpha equals 2, for instance, radius alpha 2, you form this large loop, and you realize that you are actually capturing this loop that goes beyond nearest neighbor. So it can really capture any topological feature across the system, right? And then you track and you see that at alpha 3, you form another loop, and at alpha 4, you form another loop, the yellow here, but somewhere between alpha 3 and alpha 4, the turquoise loop disappears. So you record its birth at alpha 3 and its death at certain alpha between alpha 3 and alpha 4. Okay, and you can basically form any loops or cavities or connected components that are formed in the cell.
Sorry, which loop does? I can't see that.
So you can see this turquoise loop here, right? So when these grains are basically inflated, right? More and more, this loop that you have in the middle, the white little region here, it kind of disappears because all these circles or discs overlap beyond this point. Okay, so as soon as you have contact here, you form a loop, right? The loop is when everything is connected. You follow?
Yeah, I see the birth. I just can't see where the loop is dying.
So this turquoise loop, the triangle, involves these three discs, right? So you keep growing this disc, right? And then this cavity, this hole here disappears.
Okay.
Right? And then that's when it dies. So you basically track the birth and death of these loops. So this is just an example of the loop, right? So you can do the same thing with cavities in 3 dimensions. And in lower dimensions, you can do the same with connected components. How many components are related? And yeah, so this, I didn't mean to go through all these details. So you can immediately apply this to your packings, disordered and amorphous. So I'll show you back and forth. So you can see that the persistence diagram of these two, as persistence diagram for the loops for these two packing is significantly different, while the packing density is changing only by 4%. Right? So you have the amorphous at 63%, and you have the partially crystallized packing at 67%. Right? So now the question is, what does this mean? So it is reduced in terms of complexity, hopefully, from that the full structure of packing. So now we need to understand this. So as it turns out, we had a very good student from Japan, and he figured out that more than 99% of the points in the persistent diagram, they belong to certain areas that can be fully quantified. Okay, so I'm aware of time, so I'll go quickly through this part. So I won't go through. So I can talk to you guys later on, since we don't have a lot of time, what this means. So you can actually fully quantify the evolution of the structure in terms of tetrahedral and polyhedral deformation by just looking at these persistent diagrams and the areas where they are mostly populated. So in other words, so the areas where you have high concentration of points are the areas where you have most of the mechanism that the packing undergoes during this transition from disorder to order. Okay, so we were able to identify 4 different mechanisms by just looking at these persistent diagrams that facilitates densification from disorder to order. Okay, so these are the 4 kind of mechanisms, D1 to D4, and each of them represents the transformation at a local scale from tetrahedral and octahedral configuration of grains into full disorder or less dense. Okay, so I can show you D1 looks like this, D2 looks like this, D3 looks like this, and D4 looks like this. So D3 is an interesting one because it's the breaking of an octahedron into 2 tetrahedron. Okay, so this is good. So we have a better understanding of what happens when you're not looking at dense local tetrahedron. Okay, so essentially the deformation at the grain scale that facilitates compaction in your system. Okay, but we still don't really know much about the large-scale crystallization process. For that, you need to identify FCC and HCP in your structure. Okay, so it turns out that this persistent homology, in the form that I presented to you, is unable to distinguish between FCC and HCP. So we had to go a little bit higher. So with the knowledge that that FCC and HCP, they both have octahedra and tetrahedra, and naturally they leave identical signatures in the persistent diagram in a normal form. However, the way that these octahedra are arranged are different in FCC and HCP. So in FCC, what you have is tetrahedra in a unit cell that are arranged in the corners just around surrounding the octahedron. Okay, and these tetrahedra can only and only connect via an edge in the middle. Okay, so whereas in HCP you will have these edge connected tetrahedra, but this tetrahedron will be connected to another tetrahedron in the unit cell above via this face. Okay, so with that in mind, we can go to higher order resistant homology. So what I showed you earlier was the union of two spheres or disks, but if you look at the union of 3 disks or union of 4 disks and track the topological features that are created, you will be able to identify you'll be able to disseminate FCC and HCP. So this is an example of 3 cover folds, and it turns out that the minimum K or the smallest K that you need to distinguish between FCC and HCP is when you consider the evolution of the topological features of union of 4 spheres. So I won't go through all the details. You're standing up.
Just gently telling you.
Yeah, sure. So I can skip this. So I'll just show you the results. So you can do some math gymnastics, and you can identify FCC and HCP that every single grain is involved in. So what are the surrounding structure in terms of FCC and HCP that every grain is involved in? And if you do that, you will see that as you increase the density of the packing, FCC prevails, okay? And this is a fairly robust analysis, and we basically, I won't go through the details here, but we basically made sure that everything is considered here. So in hard sphere packing that I showed you, it looks like based on the protocol that I presented, FCC prevails as the packing density increases. But this is a bit of a debate, and it has been for a long time. I think recently Stefan and colleagues showed that there is no really energetic argument why FCC should prevail. So we know that FCC prevails in a lot of dry systems, in also some foam system, but also in some other dry granular systems, HCP prevails. And this is really, there is no argument for one or another, okay? So we know that FCC has higher number of slip systems, but we tested all of that and we didn't really see an advantage in that sense. So since I don't have a lot of time, I just show you this graph here, which is based on 4 cover persistence homology. And what we show here through simulation, as well as experimental data we have, is that when you start from a regular packing, FCC or HCP, and you try to melt it through shear, it looks like FCC is more resilient and less prone to melting or changing its pattern compared to HCP, for the same amount of shear, for the same amount of energy that you put into the system. So still not really a very strong argument why FCC prevails, but our observation mixed with DEM shows that FCC is prevailing structure. So I think I can stop here. Yeah. Thank you.
Couple of questions.
Yeah. I ran a bit fast. No, so it's good. So I'm happy to talk. I mean, some of the tools that we have, they can be useful. So they're tools at the end of the day. But really, I didn't really show you a lot of results.
Maybe I can ask a question.
Yeah.
in these patterns, when you have a boundary, like a cylindrical boundary, a spherical boundary, the order close to the boundary can be very different, like shell-like ordering.
Yes.
And most people sort of discard that because they want to study the bulk. But have you ever thought of just looking at that? Oh, you have the data already, but have you ever thought of looking just how the transition from?
That's the first thing we do. We chuck them out immediately.
You chuck it in.
So that's a really an interesting point. So we do get rid of them, but we have in the case of cylindrical and spherical geometries, we have curved boundaries.
Yeah.
And there is a wealth of data there. So we actually, while we get rid of them, we're always fascinated in the deformation of the crystals that are formed as you go away from the boundaries. So we have them all sitting somewhere in the bin, but the bin is there. Yeah, that's a good point. Yeah, good.
You set fire to the big.
No, that's it.
Did you use a specific measure to compare your Pacific diagrams? Like compute some distance, some Wasserstein distance, or something?
So these are all based on alpha shape synthesis, and they are based on weighted Euclidean distance. So you form your simplices, the only structures, but the distances you measure, they are based on Euclidean, but also weighted by the radius of the sphere that they are being measured on. So weighted Euclidean distance, essentially.
I don't think that I really meant this. So
Okay.
if you look at your persistent diagram to
Yeah.
Korea, then just your point is so this one. So if you want to
This one?
compare one with the other. So
Okay, maybe this one.
no.
This one, Jimmy?
Yeah, so how do you compare the first and the second class?
You mean how we go about to quantify this?
Yeah,
So that's all the details that I skipped. So what you do here, so you basically measure the population of certain spots, the hot spots in your persistent diagram. So what you can do, you can fit a Gaussian probability distribution over any of these hotspots, and you can measure the distance that every point within that probability distribution has to these values that can be theoretically, analytically calculated, and you can weight that distance. And if a point is here, it belongs to an octahedron. If it's further away, based on this Gaussian distribution, you can, based on the distance it has from that analytically calculated point, you give it a different amount of weight, and you can identify how many tetrahedra, octahedra, or FCC, HCP I have in the system. So that's how you robustly can measure.
and this you compare then with the other.
Yeah, so you have full crystal, you can create full crystal FCC or HCP and compare it to these experimental patterns.
Fine, that's good.
You showed this graph to K, where it was constant to start with, and then it decreased as you went through the banal density, and then something which I didn't understand happened.
It plateaus and goes up again.
Yeah, you understand why that's the thing?
So the best I can say, well, that's certainly one of the yeah, here. So I try to paint a picture from contact perspective. Okay, so this K is connected to a specific heat. So how much temperature, if you have a thermal system, how much the temperature goes up if you inject certain amount of energy. So this K can be connected to a specific heat. And it turns out that volume alone cannot capture that. So it's the contacts that can capture that. And in the sense that the contacts per grain become important, so you get mechanical contact that doesn't change, even though you have their numbers fluctuating and increasing as you go through densification. And at the end, you get this mechanical contact increasing. Okay. So while you don't get any particular feature in the geometrical contact, what you get is this change of the fluctuation of contacts. And this is what we think is responsible for the specific heat or K that is not universal anymore. So it is kind of between certain ranges, it behaves different. But that's a good question. So a lot of, so we can possibly go deeper with numerical analysis on this.
Can you say what should happen in the limit to blue
You mean what value of K we should have?
at 74%?
Analytically, you mean? Should be possible to calculate. A good one. Yeah. Okay.
So do you think that the occurrence of FCC preferentially in your system may have to do with friction? And I suppose the reason why I'm asking that is because when you densify beyond Bernard's RCP in Lomacevsky-Dirichlet algorithms without friction, then you might get better.
I don't. So the truth is that I don't know the answer to that. So what you get below Bernard is that friction, as long as your spheres are the same diameter, friction is what determines your jamming density, and that is highly reproducible. But above that, when you have a mixed kind of partially crystallized, a mix of disorder and order, there is not a single point that you can identify clearly that is reproducible and achievable. So I showed you a picture of what happens to the contacts. So the mechanics of the system is really in chaos a little. So while the mechanical contacts remains more or less constant, you get this geometrical contact increasing rapidly, and then you get this fluctuation of the spread of the contacts. So I suspect that the way that they arrange locally can play a big role. So friction would be a parameter, but I can't really say for sure that is the key. So possibly, I mean, we know that if you do epitaxial, in the sense that, what Matthias Schroeter and colleagues do, if you do simple shear or various types of shear, you will get still FCC as well. And they also play with different beats and also different media as well. So I don't really know if this is universal.
Yeah, and my second question would be, so on that graph, you are suggesting that there are at least two regions beyond RCP,
Right.
The bright yellow and the bluish one.
Mm-hmm.
So when people have looked at the question of what happens at RCP with more geometric measures, rather than counting ring numbers, but rather looking for similarity to FCC-like or HTTP-like environments. And of course, geometrically, you do find, at least in frictionless particles, sudden onset of those FCC-like or HTTP-like local domains geometrically. But I'm not aware that geometrically there's any other distinction happening between your bright yellow and your blue phase. So have you got any comment on that?
So again, I want to bring the picture from mechanics. So yes, friction essentially plays a role in specifically in the mechanics of the system. Okay, so in that region, what we see is that the mechanical contact remains, it plateaus, so it remains more or less constant. And while the mechanical contact begins to rise in this part. And my suspicion is that friction in this range plays a bigger role than geometric compactification in this range. I think the picture is a lot more complex. It's an interplay between geometry and mechanics, especially in the experimental patterns. But yeah, I think these things can be probed by DM with similar experimental properties. So yeah, so in this range, of course, you still have universality of the volume distribution as you do for disordered packing, which is again weird. You shouldn't, because it's not a reproducible range.
Okay, thank you, Mohammed.